Okay, hello everyone. So, to continue with architecture, we're going to start looking at number systems, right? Number systems. So, at this point, we're all used to working with the base 10, right? Base 10, which is 0 to 9, and then we start, of course, to 10 to 19, 20 to whatever, right? We're comfortable with working with base 10. But then, computers don't know 5, they don't know 3, they only know two numbers, zeros and ones. So how are we able to move from zeros and ones to representing stuff like this, right? 5 and 3s, hello, letters, etc., etc. So we're able to move from just zeros and ones to going able to do this. Well, we're going to discuss a bit about that right now, right? So, we're also going to start with base 2. Base 2. Right? Or binary, right? Or binary, as it is most commonly called binary. So binary, as I've discussed, it's only known we only use two numbers, zeros and ones. And then since this is in base 2, I'm going to take a base 10 example just before we go any further. So from grade 1, we've talked about ones, tens, hundreds, thousands, etc., etc., right? Now, this in base 10 is just 10 to the power 0, right? 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, right? And we keep on going and going and going up to infinity, right? Now, there's a similar thing in base 2, because, for instance, in base 10, if I wanted to say represent 15, what do I have? In the tens place, of course, I would have a 10 there, right? I would have a 10 there, and then there I would have a 5, and then if I add these together, they give me a 15 over there. So we have a similar thing when we start working with base 2, but since base 2, of course, we're working with the highest number working with here is 2. So instead of 10 to the power 0, 10 to the power 1, 10 to the power 2, etc., etc., what we have is 2 to the power 0, 2 to the power 1, 2 to the power 2, and then 2 to the power 3. I'm going to end here for now, then we're going to further expand as we keep on going, right? So how you see this mostly represented in most cases is 1 to the power 0, this is 1, this is 2, this is 4, this is 8, and then we just continue doubling this, so we would have 16 here, 32, etc., etc. So now, how do we convert numbers, right, from normal base 10 to binary and vice versa, right? So say for instance I have a 10 there, right? I have a 10. So how would I represent this 10 in binary, right? Well, one way of doing it, the way I like doing it, is basically I just see what's the closest power of 2 here, right? What's the closest power of 2 that we have here? The closest power is 8, so I put a 1 on 8 there, right? And then when we say 10 minus 8, what does that give us? 2, right? What's the closest power of 2 that's equivalent to 2? Of course, it's just 2 itself there, right? Minus 2, that gives me a 0. So everywhere else here, I can just place a 0. So this is how you represent 10 in binary, right? Then to convert back, all you'd have to do is that you just have to get 1 by 8. So 1 by 8 plus 4 by 0 plus 2 by 1 plus 0 by 1, which if we add these two together gives us back our 10 there, right? So this is one way of conversion using these values that we already have here, these place orders. And the bigger your number is, so let's say for instance if our number was say, yeah, as we keep on going, so we have, let's say, 2 to the power 4 there, 2 to the power 5, and then our numbers keep on getting bigger and bigger as we work with more bits, right? Okay, so the other way of conversion, so we go back to our 10 there. The other way of conversion is through constant division. So what we do is that we get 10 there, right? Divide that by 2, right? What's that there? So first of all, we know it's 5 remainder 0, right? So we keep the remainder there as a 0. We have 5. We divide by 2. What's that there? The answer there is 2, and what's our remainder? Our remainder is 1 there, right? We divide this by 2 again, right? 2 divided by 2, that's that's 1 remainder 0, right? What's 1 divided by 2? It's 0 remainder 1. Then we read this in this format, right? Which then gives us 1 0 1 0, which is what we had here, right? So this is how we're able to convert from binary to decimal. So it's just the basic, it's just the basics of binary and base 2. Right? As we go on, of course, we're going to talk about how we represent negative numbers, decimal points, etc. But for now, that's all we need to know. So I'm just going to try out to convert a few more numbers using both methods so that we're a bit more comfortable with them. So I'm going to convert something like 15, 20, 15, 20, and just say 11. Right? I'm just going to convert these numbers real quickly. Okay. So using first of all, I'm going to do all of these using first of all the division method, no, the box method, and then we'll do the division. Okay. So to draw up our box, I'm going to draw up our box there. Then when I say okay, 1, 2, 4, 8, right? I can also add 16 there. Right. Okay, so now draw that there. Okay, so we look at 15, right? We look at 15. Right. So what's the closest power? What is the closest power of 2, right? That is less than this one. Of course, it's 8, right? That's the closest power of 2 that we have. That's less than 15. So we can put a 1 there, right? So here we're converting 15. So what's 15 minus 8? 15 minus 8 is 7, right? What's the closest power? What is the closest power of 2, right? That is less than this one. Of course, it's 4. So minus 4, that gives us 3. And then we continue. What's the closest power of 2 here? Closest power is 2 itself, 1. Minus 2 there. What we do there is that we get a 1 there. Closest power is 1 there. 1 minus 1 gives us a 0. So this is how you represent 15. And one thing you know is that we call these individual things bits. We call these bits. And what you notice is that in 4 bits, right, with these 4 bits, the maximum number that we can represent with these 4 bits is 15 if all these are 1s. Right? So the range of this is basically 0 to 15, or 0 to 2 to the power 4 minus 1 there. So this is just one thing you might try to remember. And in short, for any number of bits that were given, so let's say we're given n bits, right? Under normal representation, the highest number you can represent is 0 to 2 to the power n minus 1 there, right? It's the biggest number we can represent for any given number of bits. So we go on to 20. What's the biggest power of 2? That's less than this one. Well, the biggest power of 2 is 16, right? So we're going to add a 1 on 16 there. I'll add the 1 on 16. Then what's 20 minus 16? Right. 20 minus 16 is 4, right? What's the closest power of 2 to 4? It's 4 itself there, so I can put a 1 on 4. So 4 minus 4 there is 0, right? So meaning nothing else. So 16 plus 4 is 20. So I can just put zeros elsewhere here. So then this is the binary representation of what? Of 20. Then we go to 11, right? So you can try out the conversion to 11. It's a very trivial one. But then what we're going to do is we're now going to use the division method, right? We're going to use the division method. So I'm going to say 15, right? How are we going to do it with 15? 15 again, we're going to say, okay, 15 divided by 2, right? What's the answer? This is equal to 7 remainder 1. Right? So remainder 1. What's 7 divided by 2? This is 3 remainder 1. Right? 3 divided by 2, 1 remainder 1. Right? Then we're going to have, okay, what's 1 divided by 2? This is then 1 remainder 1. What do we do afterwards? We read it up, we read it going upwards like that. Why am I even using a highlighter, for goodness sake? we read it going upwards like that, right? So our binary is 1 1 1 1, which is what we got here, right? Which is what we got here, 1 1 1 1. That's the binary representation of 15. Then we try again with 20, right? What is 20 divided by 2? 20 divided by 2 is, of course, this is 10, remainder 0, right? What's 10 divided by 2? This is 5, remainder 0. Right? 5 divided by 2, this is going to give us what? This is going to give us 2, remainder 1. What's 2 divided by 2? Right? It's 1, remainder 0. 1 divided by 2, this is equal to 0, remainder 1. We read it upwards again, which gives us 1 0 1 0 0. Same thing. So when it comes to converting from decimal to binary, it's a matter of knowing. It's just a matter of well, whichever one you're comfortable with. Whether you're comfortable with using this box or you're comfortable with doing the division. I personally like using the box because with this I can convert either from binary to decimal, right? Because I can just look at my binary here, right? And then just say, okay, 0 times 1, that's a 0. 0 times 2, that's a 0. 1 times 4, that's a 4. 0 times 8, that's a 0. 1 times 16, that's a 16. I add those two together, which gives me back a 20, which is what this is, right? So again, it just depends on which one you're comfortable with using between the two, right? And then just to demonstrate this, I'm just going to do some conversions backwards, right? We can have 0 1 0 1 0 1 1 1, and then 1 0 1 1 0 1, like that, right? Just to demonstrate what we have here. So the first one we're going to do is this one, 0 1 0 1. And what I said, it's just powers of 2. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So it depends on which one you're comfortable with using that. So you know the highest power here is 2 to the power 3. So you can say 2 to the power 3 times 0, right? Plus 2 squared times 1 plus 2 to the power 1 times 0 plus 2 to the power 0 times 1 there, right? Which is just 4 times 1 plus 1 itself, which is 5. So this is 5 in binary. Same thing for this one, 0 1 1 1. This is equal to, and you can always omit these that have zeros anyway, that's just an extra step, but you can have 2 to the power 3. So just for the sake of demonstration, I'm adding those there, right? 2 to the power 3 times 0 plus 2 squared times 1 plus 2 to the power 1 times 1 plus 2 to the power 0 times 1. So I'm pretty sure in the IAS sim you've been seeing these ones and zeros, so at least at this point it's a bit obvious for how to convert these. Quite right, in the IAS it's been 8 bits, so 0 0, so you just have to go from 2 to the power 0 to 2 to the power 7 when you're doing those conversions, right? So from here we're going to say, okay, this is 4 plus 2 plus 1, which gives me 7, right? Then we also have to do the same thing for this guy over here. Now for this one I'll use the box anyway. Again, it's the same thing, just depends which one you're comfortable with. For this one I can just use the box and do that. So this is me just showing you how you can do using all the different methods that we have learned so far. So I have 2 to the power 0, which is 1. So 1 2 4 8 16 32. 1 2 4 8 16 32. Now we're going to put our binary there, 1 0 1 1 0 1, right? Then I just add those two, and then I'm just going to add those. So I just have to add those together, right? Which is just 32 plus 8 plus 4 plus 1, which if I'm not mistaken is 40 45 there, right? So again, it's up to you however you want to do this, right? It's up to you however you want to go around solving these questions. but personally I prefer the box. So just to end off this video, I'm going to leave you with just a bit of practice, right? So first of all, the first part is going to be converting from decimal to binary. So I'm going to give you 25 7 25 7, then we got 64 130. Yeah, then another one from binary to decimal. So from binary to decimal, we're going to have 1101 0101. Write it on this one. We're going to have 1111 0101 1001. So just some basic ones. As I said, if you have 8 bits like this, so 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7. So if you use the box, the maximum number will be 2 to the power 7. But all the conversions, it's just the same way of doing it, and just add everything. So you can just try doing this. Yeah, and then see, this is just basics of binary. Next thing we're going to look at is hex.